Now we are going to deal with the module 5. It is material science, QFET assumptions and Fermi level. Now what is QFET? Quantum free electron theory and assumptions. In the previous sessions we have seen that there are certain failures in CFET, that is classical free electron theory. The 3 points we have discussed the failures. Now we are seeing the quantum free electron theory, the assumptions. The energy values of conduction electrons are quantized. The allowed energy values are realized in terms of set of energy values. That means energy values of conduction electrons are quantized. Energy of an electron is quantized. So this quantization has come with the quantum free electron theory. Next assumption is the distribution of electrons in the various allowed energy levels occur as per the Pauli's exclusion principle and also obey Fermi-Dirac quantum statistics. So these two assumptions, which the energy levels of electrons are quantized and the distribution of electrons in the various energy levels is as per the Pauli's exclusion principle and also obey Fermi-Dirac quantum statistics. We will see further what exactly it means. So the free electrons travel at a constant potential inside the metal but stay confined within the boundaries. Next assumption is the attraction between the free electrons and the lattice ions and the repulsion between the electrons themselves are being ignored. If you look at the CFET assumptions and QFET assumptions, the first 2 points are being considered of greater advantage, which led to the success of the QFET. That is, all the failures of CFET could successfully explain in the quantum mechanics. So there was a success with the quantum free electron theory. To understand the concept of quantum free electron theory, the assumptions, the first 2 assumptions has been changed. So the third and fourth assumptions which we have seen in CFET remains the same as with the QFET. So first 2 points led to a drastic changes and which could explain all the failures of CFET were successfully explained with the QFET. Next, density of states. It is defined as a number of available states per unit energy range centered at a given energy E in the valence band of a material of unit volume. It is denoted by GE. What exactly is the density of state? That means number of energy levels lying between the energy state E and E plus DE. The product GE DE gives the number of states in the energy interval DE at E. GE represents the energy of density of states at a point E. As DE is small, it is assumed that GE is constant between E and E plus DE. That means, what are the possible energy levels between E and E plus DE? DE is a small increment with that of the energy level. The density of states in the range E and E plus DE is denoted by GE DE. That is nothing but what are the number of energy levels lying between E and E plus DE, denoted by the expressions. For your level, you just need to know the expression itself, no need of derivation. So GE DE is equal to 8 root 2 pi m to the power of 3 by 2 by h cube into e to the power of 1 by 2 dE, or we can say that 8 root 2 pi m to the power of 3 by 2 by h cube into root e dE. Next, what exactly is the Fermi-Dirac statistics? In the first slide, I was telling you the second assumptions, that Pauli's exclusion principle and Fermi-Dirac statistics. Now we will see what exactly is a Fermi-Dirac statistics. Under thermal equilibrium, the free electrons acquire energy obeying a statistical rule known as a Fermi-Dirac statistics. What exactly is Fermi-Dirac statistics? We will see. Fermi-Dirac statistics is applicable to assembly of particles which obey Pauli's exclusion principle. So Fermi-Dirac statistics are a set of statistics which are obeyed by the particles which obey Pauli's exclusion principle. So here we have seen that electrons obey Pauli's exclusion principle. Therefore, electrons obey Pauli's exclusion principle implies electrons has to obey the Fermi-Dirac statistics. They must also be identical particles of spin 1 by 2 and are indistinguishable particles. As electrons satisfy these two conditions, they have to obey Fermi-Dirac statistics. As I said the electrons are identical particles of spin 1 by 2 and are indistinguishable. So electrons satisfies, they are obeying the Pauli's exclusion principle, and the particles are identical of spin 1 by 2 and are indistinguishable. Therefore, electrons has to obey the Fermi-Dirac statistics. Fermi-Dirac statistics permits evaluation of probability of finding electron occupying an energy levels in certain energy range through a function called as a Fermi factor denoted by f of E. F of E is called, E is denoted, it is a Fermi factor F of E, which gives the probability of finding a particle occupying an energy level. So it is given by the Fermi factor F of E. According to this theory, the free electrons are quantum particles. The distribution of electrons amongst various energy levels is in accordance with the Pauli's exclusion principle. So the number of conduction electrons per unit range per unit volume is given by NEDE is equal to GEDE into F of E, where F of E is nothing but a Fermi factor, GEDE is nothing but a energy density of states, which we have seen in the previous slide, and Ne is nothing but the number of electrons or the free electron, the distribution of electrons amongst various energy levels is in accordance with the Pauli's exclusion principle, the number of conduction electrons per unit range per unit volume. So NEDE is nothing but number of electrons per unit range per unit volume. So what is Fermi energy? The energy corresponding to the highest occupied level at 0 degree absolute is called as a Fermi energy, and the energy level is referred to as a Fermi level. This is a very important definition. So Fermi energy is nothing but the energy corresponding to highest occupied level at 0 degree absolute. That means what is the energy at 0 degrees absolute temperature at 0 degrees Kelvin, the energy corresponding to the highest occupied level, that energy level is called as a Fermi level. If you see at the figure here, at temperature T is equal to 0 Kelvin, the highest occupied energy level is called as a Fermi energy level, and this is denoted by EF. EF is given by h square by 8m into 3n by pi whole to the power of 2 by 3. What is Fermi energy? It is the highest occupied energy level at T equals to 0 Kelvin. Absolute 0 is nothing but 0 Kelvin. That energy is called Fermi energy, and the energy level is called as a Fermi energy level, denoted by EF. Next we see the expression for the Fermi energy. According to Fermi Dirac theory, the total number of conduction electrons per unit energy range per unit volume is given by N of E is equal to 0 to infinity GEDE into F of E. I have explained here in this previous slide. So NEDE is equal to GEDE into F of E. The same expression we are going to use here in the expression for Fermi energy level. GEDE into F of E. Number of conduction electrons, Ne. So the same expression we are writing here, and we are going to see the applying the limits, and we are getting the expressions. So this is the equation. If you take the Ne is equal to integral of 0 to infinity GEDE dot F of E is equal to integral of 0 to infinity GEDE is nothing but 8 root 2 pi m to the power of 3 by 2 by h cube into e to the power of 1 by 2 dE, and F of E is taken as 1. So at 0 degrees what is happening here? Probability of an electron occupying is 1. So we are taking as 1. F of E is 1. At 0 Kelvin, the top of the electron energy distribution is defined as EF. What is the Fermi energy expression? What is the Fermi level? Highest occupied energy level at T equals to 0. So the limit, we are taking the upper boundary of the limit as 0 to EF. So the integral becomes n is equal to 8 root 2 pi m to the power of 3 by 2 by h cube into 0 to EF, because the highest occupied energy level is EF. So 0 to EF, e to the power of 1 by 2 is equal to, because everything we have taken it out of the integral because it is a constant value, and 0 to EF root E dE is taken as 8 root 2 pi m to the power of 3 by 2 by h cube. In doing integration under the limit 0 to EF, we are getting 2 EF to the power of 3 by 2 by 3. So rearranging the terms, getting the expression, getting the value of EF, EF is equal to h square by 8m into 3n by pi whole to the power of 2 by 3. This is the same thing I told you here. EF is equal to h square by 8m into 3n by pi and whole to the power of 2 by 3. So that derivation we have done here. Next, what is Fermi temperature? It is a temperature at which the average thermal energy of a free electron in a solid becomes equal to the Fermi energy at 0 Kelvin. It is denoted by TF. So TF is equal to EF by K, where K is nothing but the Boltzmann constant. Fermi temperature is a temperature at which the average thermal energy of free electron in a solid becomes equal to the Fermi energy at 0 Kelvin. 0 Kelvin. It is called as a Fermi temperature. Next is a Fermi velocity. The velocity of the electrons which occupy the Fermi level is called as a Fermi velocity. What is Fermi velocity? The velocity of an electron which occupy the Fermi level. The velocity with which it is sitting in the Fermi level. That velocity is called as a Fermi velocity, denoted by Vf 2Ef by m under root, or Vf is equal to 2Ef by m whole to the power of 1 by 2. Now next is expression for electrical conductivity in metals. Free electrons obey Fermi-Dirac statistics. Applying Fermi-Dirac statistics, sigma expression for electrical conductivity n e square lambda by m star into Vf, where m star is the effective mass of electron. Sigma is equal to n e square lambda. Lambda is nothing but the mean free path. M star Vf. M star is nothing but effective mass. Vf is nothing but the Fermi velocity which we have defined before. So sigma is equal to n e square lambda by m star into Vf, where m star is the effective mass of electron.